Hello again. Let's dig deeper into the biological treatment principles that are used to design bioreactors for on-site wastewater treatment. In other words, what are the principles by which we determine the dimensions of such reactor and its capacity to treat or remove pollutants? In the following slides, we will demonstrate these principles for the biodegradation of organic matter. Well, the dimensions of a bioreactor are mainly determined by the pollutant input load, in this case the organic matter load, the targeted output organic matter load or concentration, and the degradation rate. The input load is dictated by the population size and the activities in the site, while the output load is dictated by regulations. Interestingly, typical biological degradation rate was empirically found to be logarithmic and can also be described by either zero or first-order kinetics. Zero-order kinetics refers to a constant biodegradation rate that is independent of substrate concentration. So in our example, it means that the reduction of organic matter over time will be constant regardless of its concentration. Zero-order kinetics is typical for higher concentrations. First-order kinetics refers to an increasing degradation rate as a function of substrate concentration. Or, as in our example, the degradation rate increases with increasing organic matter concentration. This kinetics is more typical for lower concentrations. The empirical Monod equation for substrate degradation, or in our case, organic matter degradation, describes this concept well. It can also be seen graphically and will be further explained. As you can see, the degradation rate Q is a function of the maximal degradation rate, Qmax, multiplied by the concentration of the substrate S, which in our example would be organic matter, over the substrate concentration plus the constant Ks, which is the half saturation constant. Both Qmax and Ks are determined experimentally. An examination of the Monod equation reveals that it pretty much combines both zero and first-order kinetics as follows. When the organic matter substrate concentration is much smaller than the Ks, the S in the dominator can be neglected, and the rate follows a linear equation. Or in other words, it follows first-order kinetics. And when the substrate concentration is higher, Ks can be neglected, and the rate is constant and equal to Qmax, thus following zero-order kinetics. Since we're discussing biological systems, the rates and reactor performance are affected by a range of physical, operational, environmental factors that overall reflect the degradation efficiency. These, for example, can be reactor and media type, hydraulic loading and retention time, organic loading, aeration capacity, sludge age, nutrient concentration and availability, and environmental factors such as pH and temperature. These factors eventually determine the overall degradation efficiency and the level of degradation that can be defined as primary degradation, which refers to a minimal amount of change, or at the other extreme, it can be termed ultimate degradation, which refers to a complete conversion of the organic matter to inorganic matter. However, most often, we would aim at acceptable degradation, which refers to degradation that eliminates harmful material and that meets relevant standards. Formulating the information on the reactor's input and output loads and the reaction rates into a mass balance analysis would allow one to determine the size of the reactor and to predict its performance. Lastly, taking a mass balance approach will allow day-to-day operation of the treatment process, monitoring of the operational efficiency, and making calculations for the design and development of the treatment process. As this example shows, to calculate the mass balance, we consider the following components: the mass of the organic matter that enters the bioreactor at a certain time, which is represented by the raw wastewater concentration multiplied by the flow rate Q, which represents the volume per unit of time, the mass of organic matter that leaves the reactor, which is represented by the treated wastewater, and an accounting of the changes in the degradation or formation of organic matter in the bioreactor. Thus, overall, we can say that the change in mass over time is equal the mass entering the reactor minus the mass leaving the reactor, plus or minus the changes in that mass that occur in the bioreactor. When we operate a bioreactor to treat wastewater, we often try to work in a steady state mode. This means that the overall change equals zero, or in other words, that all the introduced organic matter is degraded so that the output mass and concentration is constant and meets the requirement. In practice, a completely steady state scenario is hard to achieve, but one can approach it. Formulating the information of the reactor's input and output loads and the reaction rates into a mass balance analysis would allow one to determine the size of the reactor and to predict its performance. To summarize, on-site wastewater treatment is based on a range of reactors which typically involve physical, biological, and disinfection components. The biological components is often the core of these reactors, and their design and operation are based on mass balance approach and the understanding of the biological processes that they aim to achieve. Interestingly, for on-site wastewater treatment, much is still based on experience and rules of thumb. For on-site treatment of domestic wastewater, we typically choose either BOD, COD, or TSS as the design parameter. In the next presentation, we will describe typical on-site treatment systems.